Hello everyone, welcome to the Learning Cubicle. In the previous class, we have learnt about the applications of convex and concave mirrors. While we were learning about applications of convex and concave mirrors, the characteristics of the image varied with the change in the position of the object, which we have already learnt in the image formation of concave and convex mirrors. Now, as we already know that as the position of the object changes, whether in case of a concave mirror or in case of a convex mirror, the characteristics of the image is going to change, which means the size of the image is going to change, the position of the image is going to change. Now, we can learn them or we can know them practically by conducting an experiment using those mirrors. But how to deal with these situations when we are not actually doing the practical experiments with those mirrors? Can we do them theoretically? If we have to do them theoretically, what is the base for that? How do we know what should be the distance? What should be the position of the object? All these things, how do we know? And also the focal length varies from mirror to mirror. So how do we calculate that? So for calculation of that, we need to learn something known as sign conventions. We need to learn about sign conventions. Now, what are the sign conventions? It's like the displacement or the velocity which we have learnt in the chapter motion in the last year, grade 9. That means we take a reference point. From that point, in whichever direction the object is going, if we take that as a positive, so the opposite direction would always be negative. So we have taken it that way when we learned about displacement, right? Suppose if the object is going towards south from the reference point, then the direction towards north would be negative. Suppose if the object is going towards east, then towards west would be negative. So much the same manner how we have learned about the distance and displacement concepts in grade 9, we will be learning about the object distance, image distance, focal length, height of object, height of image, all of them from a reference point or a reference line. This takes you back to those terms what we have learnt about mirrors: pole, center of curvature, principal axis, center of the focal length. All of them are nothing but the reference points or reference lines which we have drawn. They are imaginary. So we will be learning sign conventions taking the pole of the mirror as the reference. Okay, and we should always keep in mind that the object is always placed on the left of the mirror. Now, when we place the object on the left of the mirror, we know that the rays of light come from the left of the mirror, because for us the object is the source of light. So all the distances are measured from the pole parallel to the principal axis. That's how we take it. Now, why should we take the object only on the left? Why can't we take it on the right? And why should the rays of light be coming from the left? Why not from the right? It is for the simple reason that we read from left to right. The general script that we write is from left to right, or we read from the left to right. So the rays of light are also drawn from left to right, which is convenient for us. So always the object is placed on the left, and the rays of light also come from the left. Okay. Now coming to the actual sign conventions. The first point is all the distances from the pole and towards the left are taken as negative, and all the distances from the pole and towards right are taken positive, and all the distances perpendicular and above the principal axis, they are taken as positive, and all the distances perpendicular and below the principal axis are taken negative. Now why? negative, positive, positive, negative. Why are we giving those signs to them? How can we understand them? So we can understand them if we remember the Cartesian plane or the coordinate axis that you people are familiar with. That is something I tried to draw over here. This is the Cartesian plane. Okay, this is the origin where we have the pole. So pole serves as the origin for us. That's why I said all the distances from the pole and left are taken negative. All the distance from the pole on the right are taken as positive. And we know that this is the positive side of the x-axis in the Cartesian plane. This is the negative side of the x-axis. So that's why these distances are positive, I said, and these distances are negative, I said. Similarly, this is positive side of y-axis. That's why these I told as positive side of y-axis. And this is the negative side of y-axis below. That's why these distances are negative, I said. Okay. So all the distances from the pole on the left are taken negative. All the distances from the pole and towards right are taken as positive. All the distances perpendicular and above the principal axis are taken as positive. All the distances perpendicular and below the principal axis are taken as negative. So these are the sign conventions that we follow while we measure different distances like object distance, image distance, height of object, height of image and focal length. Now we are going to learn about the outcomes of the sign convention. That means how does the image distance, object distance, focal length, height of object, height of image are going to vary for the two spherical mirrors, that is concave and convex mirrors, is what we are going to see now. Right. So we have two different types of spherical mirrors, concave and convex mirror, you can see here, and I have written some alphabets over here, U, V, H, O, H, I and F. Okay. F is something which you are familiar with, that is focal length. H, O, height of object. H, I, height of image. U, object distance, means distance of the object from the mirror. From the mirror in the sense from the pole, because pole is the reference point for us. And V is the image distance, that is distance of the image from the pole or from the mirror, whatever. So now we will be getting the outcomes of the sign convention, whether U will have a positive sign, V will have a positive sign or negative sign. Similarly, these all for concave and convex, how are they going to change is what we are going to learn in this outcomes of the sign convention. Now, how are these helpful to us? These are helpful to us in solving the numerical problems. That's what I told. Theoretically, we will be finding out the focal length and various other quantities which are given in the numerical problem. Right? Now coming to the first one, object distance, which is U. Object is always placed on the left of the mirror, I said, on the left of the mirror from the pole. So I have already told you in the sign conventions that all the distances from the pole and towards the left of the mirror are considered negative. So whether it is concave mirror or convex mirror, image object distance is always negative because that is placed on the left. Now coming to V, which is image distance. Concave mirror forms the image on the left. Out of the 6 cases, concave mirror forms the image on the left in 5 situations. In 5 of the situations. Okay. So in 5 of the situations it is negative, except one case is what I am going to write here. Because out of the 6 cases, 5 cases it forms the image on the left, and in 1 case it forms the image on the right. That's why I have written negative except one case. Now convex mirror, it always forms an image on the right, behind the mirror. So convex mirror, the image distance is always positive because the distance from the pole on the right is positive. Now coming to height of object. In the image formation or in the geometric images we have seen, we have always placed the object like this. So it is perpendicular and above the principal axis. Distance above is always taken as positive. So height of object is always positive. Okay. Now coming to height of image. Concave mirror forms an inverted image, that is like this, upside down. So it is perpendicular and below. Perpendicular and below for concave mirror is negative. So out of 6 images, 5 images it forms below, and in only one case it forms an image above. So I will write here negative except one case. Now coming to convex mirror. Convex mirror always forms the image above. So it is positive. So convex mirror, height of image is always positive. Now coming to focal length. This is the concave mirror here. Okay, and this is where its focus is, and this is the focal length. So where is the distance lying? It is lying on the left. So distances on the left is considered negative. So focal length of concave mirror is negative. Now we have the convex mirror here. Its focus is here. So its focal length is this. So the focal length is lying on the right. So the focal length of convex mirror is positive. So these are the outcomes of sign convention. You can see for object distance, image distance, height of object, height of image, and focal length. So using these outcomes of sign convention, we will be solving the numerical problems now. Now that we have learned sign convention, we shall now proceed with solving the numerical problems related to spherical mirrors. But before we proceed to solve the numerical problems related to spherical mirrors, we need to learn something called as the mirror formula, right? So the mirror formula for the spherical mirrors, concave and convex mirrors is one by f is equal to 1 by v plus 1 by u. So this is the mirror formula for spherical mirrors, and you do not have the derivation of this formula in your class. You will be learning it in your higher classes. So as you all know, f is the focal length of the spherical mirrors, and v is the image distance, and u is the object distance. Now that we have learned the mirror formula, we will be substituting the values like v, u and finding f, or f and u and finding v. Anything, two of them will be given, and the third one we need to find out. But during the course of image formation in case of spherical mirrors, concave and convex mirrors, we have observed that when the object is at infinity, the image was diminished to a point, and when the object was at focus, the image was highly enlarged. So there is a change in the size of the image as the position of the object changed, which means there is a difference in the size of the object and size of the image in most of the cases, except for one case where the object size and image size are same. And you know what position I am talking about. It is at the center of curvature of the spherical mirror. Now when we compare the size of the image or height of the image with the height of the object, we call it as magnification. That's called as magnification. So magnification is basically the ratio between height of the image to the height of the object. That means how big or how small is the image when compared to the height of the object. So that comparison or that ratio is what gives you the magnification. Now it is quite clear that if the magnification, that is that ratio, if it is less than 1, we can understand that the height of the image is smaller than the height of the object. And if it is greater than 1, we can understand that the height of the image is bigger than the height of the object. What if the magnification is equal to 1? If the magnification is equal to 1, then the height of the image and the height of the object are same. Not only that, there is another aspect of this magnification which is giving a sign to that, a negative sign and a positive sign. If there is a negative sign to the magnification, we must understand that the image is inverted, upside down. And if the magnification value is positive, then we can understand that the height of the image, the image is erect and virtual, of course, right? So the magnification formula, m is equal to height of the image compared to the height of the object. And also it has been experimentally found and derived also, which is also equal to minus v by u. So magnification is not only restricted to the height of the image and height of the object, but it can also be related to the image distance and object distance. So this is what the magnification formula is, and this is what the mirror formula is. And we will be using these expressions while we are solving the numerical problems, and we will be discussing a couple of numerical problems related to this mirror formula and the magnification formula. Alright, so you have just seen two numerical problems related to the spherical mirrors, and we will now learn how to solve these numerical problems. But before I proceed with the solution of the numerical problems, it is a very common conception or a common feeling of the students that they are afraid or scared of solving the numerical problems. So the biggest hurdle that they have is, I don't know how to solve the numerical problems, whether it is related to this chapter light or related to electricity or whatever. They feel that it's quite difficult. And they often forget that the theory that they have learnt and the numerical problems that they are going to solve, that they are one goes in hand with the other. They are not disjoint, they are together. So if you have a good command over theory, solving the numerical problems is just a cakewalk, right? So what I want you to do now is pay attention while I am solving these numerical problems, and if you follow these steps carefully, then it's quite easy to solve the numerical problems of any kind related to light or spherical mirrors or whatever. Now, the first and foremost thing that you have to do while solving the numerical problems is writing the given data and strictly abiding by the sign conventions, the outcomes of sign conventions. So first of all, let us write the data that is given to us, and then we will substitute in the formulae that we have just discussed. Alright, now let us read the question. An object 5 centimeter tall. So 5 centimeters tall is nothing but height of the object, and height of the object is always taken as positive. We have already discussed that. And then is placed at a distance of 12 centimeters from a concave mirror. Object is placed at a distance of 12 centimeters from the mirror, and object distance is always negative because object is placed on the left. So u is equal to minus 12 centimeters, and such that it forms an image on a screen placed at a distance of 16 centimeters. So image is formed at a distance of 16 centimeters. Now here there is a problem, okay, that is whether I should take plus 16 or minus 16. Now why does this confusion arise? First of all, when we have the outcomes of sign convention very clearly, that for every quantity that we are discussing here. But if you go through the outcomes of sign convention for concave mirrors, concave mirror forms 5 situations the image on the left, and in one situation it forms the image on the right. So concave mirror takes image distance negative as well as positive. Now what sign should I take for this is what we have to think. For that, let us go back to the question again. An object 5 cm tall is placed at a distance of 12 cm from a concave mirror such that it forms an image on a screen. So this is the key word for us, on a screen. On a screen is nothing but a real image. A real image only forms on a screen. Virtual image never forms on a screen. So real image in case of concave mirror forms on the left. So we should take V minus 16 centimeters. Okay. Now what are we asked to find? Calculate the focal length of the mirror, F. And also we are asked to calculate the height of the image, HI. So we have two unknown quantities here. One is the focal length and second is the height of the image. Okay. And we are also asked to comment on the nature of image, which I already commented. Just now I said the image is formed on the screen. So it's a real image, and a real image is always inverted. So the nature of the image is real and inverted. So we can write it over here already. Alright. Now we have U, we have V, and we have to find F. So the mirror formula which we just learnt is 1 by F is equal to 1 by V plus 1 by U. Alright. So which is 1 by minus 16 plus 1 by minus 12. Both of them are negative. So 16 and 12, the LCM is 48 minus 3 minus 4, which is equal to minus 7 by 48 is 1 by F. Therefore, F is equal to minus 48 by 7, which is 6.86 centimeters negative. Okay, minus 6.86 centimeters is the answer for the focal length. Now we have to find out the height of the image. For that we have a formula, M is equal to HI by HO, which is equal to minus V by U. Okay, HI is what we have to find and HO is 5 is equal to minus V. V is minus 16 by U. U is minus 12. Okay, and this minus and this minus get cancelled. Okay, 4 3s are 4 4s are. Okay, so HI is equal to cross multiply. HI is equal to minus 20 by 3. Okay, which is equal to minus 6.67 centimeters. This is the height of the image. Right? Now, there is a way to check whether you have done the sum correctly or not. We have that facility also over here. Okay. Now, let's see how to check that. Focal length, we got minus 6.86 centimeters. Let us take it approximately 7 centimeters. Right? So, if focus is at 7 centimeters, center of curvature will be at 14 centimeters. We know, double the distance. Okay. So, 14 centimeters. Object is at 12 centimeters. Object is at 12 centimeters, means which falls between 7 centimeters and 14 centimeters. That means between C and F. So, the object is between C and F, and according to the image formation, the image will be formed beyond C. Means the image distance should be more than 14 centimeters. 16 centimeters. So, we are on the right track. Okay, and the image is enlarged. If it is formed beyond C, the image is enlarged. Means it should be greater in height than the object. Object height is 5 centimeters and image height is 6.67 centimeters. So, the image is enlarged and we are perfect. Right, now we will look at the second numerical problem. An object 4 centimeters tall. So, height of the object is given as 4 centimeters, which is positive because the object is above the principal axis, is placed at a distance of 20 centimeters from a convex mirror. So, u is equal to minus 20 because the object is on the left, and focal length of the lens is mirror is also given over here. It is 15 centimeters. Focal length is positive because the focus of convex mirror lies on the right. We are asked to calculate the distance of image from the mirror, which is v, and we are asked to calculate height of the image, which is hi. Okay, and we are also not asked to comment anything on the nature of the image, because in both the cases convex mirror forms virtual, erect and diminished image. So that's why that question doesn't appear over here. Right, now let us try to find out v. For finding out v, we use the mirror formula. 1 by f is equal to 1 by v plus 1 by u, and 1 by f is 1 by 15, that is equal to 1 by v, we do not know that, plus 1 by u is minus 20. So this minus 1 by 20 comes this side, it will become plus. So 1 by 15 plus 1 by 20 is equal to 1 by v. Right? So the LCM of 15 and 20 is 60. 4 plus 3, that is equal to 1 by v. Therefore, v is equal to 60 by 7. Okay? Which is equal to 8.57 centimeters. Okay? Which is also positive. Okay? Now, let us find out the height of the image. For that, m is equal to hi by ho, which is equal to minus v by u. Height of the image is something we need to find out. By height of the object is given as plus 4 centimeters, that is equal to minus v. We got 8.57, but I am not going to take that because it is a non-terminating decimal. So I will take the fraction instead. So it is minus 60 by 7 by u. U is minus 20 centimeters. Okay. So this minus and this minus get cancelled here, and then we will cancel this also. 4 ones and 4 fives. Okay. So hi is equal to 60 by 7 into 1 by 5. 5 ones are 5 12s are. So we got 12 by 7. So hi is equal to 1.7 centimeters, which is also positive. Okay. So we can also check whether what we have done is correct or wrong. And in case of convex mirror, we know that the height of the image is always smaller than the height of the object. Height of the object is given as 4 centimeters and we got height of the image as 1.7 centimeters. So it's correct. And also we know that the image is formed on the right for convex mirror. So image distance should be positive, which is plus 8.57 centimeters. So we are perfect. Right, now we shall try to solve the question numbers 3 and 4, which you just saw. Let us first read the question number 3. A concave mirror forms 5 times magnified inverted image of an object placed 20 centimeters from the mirror. Calculate the focal length of the mirror and image distance. Now here in this question we are given with magnification, which is 5 times inverted. So inverted image, for inverted image we always take the magnification negative, which we have already discussed earlier. So this is minus 5, and you are asked to calculate, you are also given the object distance, which is u is equal to minus 20 centimeters. Okay, and you are asked to calculate the focal length and the image distance, both of them. So here we are given u, we are not given f, we are not given v. So you must be wondering, in the mirror formula 1 by f is equal to 1 by v plus 1 by u, we have two unknowns. You must be wondering that we have two unknowns. One is f, which is unknown, another one is v, which is unknown. We are only having the value of u. So how do we proceed with that? So for proceeding with this, we use the magnification formula, which is m is equal to minus v by u. Hi and ho we do not include over here because those values are not given in the question. Okay, so m is given as minus 5, okay, is equal to minus v by u. Okay, so if you can cancel, minus 5 is equal to minus v by minus 20, okay, and we cancel this minus and this minus, so we will get it as minus 100 centimeters. So we got v already, which is asked in the question. Alright, now we can easily find out the focal length. So 1 by f is equal to 1 by v plus 1 by u. 1 by f is equal to 1 by minus 100 plus 1 by minus 20. Both of them are negative. LCM is 100, and here we will get minus 1 and here we will get minus 5. So 1 by f is equal to minus 6 by 100. Therefore, f is equal to minus 100 by 6, which is 16.67 centimeters negative. Right? We can also verify whether our sum is correct or wrong. We all know that if the image is real and inverted, it will be formed on the left. So image distance should be negative, which we got. And focal length, we got it as 16.67, approximately 17 centimeters if we take. Then center of curvature will be at 34 centimeters. Object is between C and F, because 20 centimeters is the object distance. So image should be formed beyond C, which is more than the center of curvature's distance, which we got it as minus 100 centimeters. So we are correct. This is a different way of doing the sum, right? Right. Now let us try to solve the fourth question. What will be the focal length of a convex mirror which forms a diminished image at a distance of 12 centimeters from the mirror? This is convex mirror, and here the image is at a distance of 12 centimeters from the mirror, and we all know that convex mirror always forms the image on the right side, so it should be taken as positive. So image distance is given clearly over here, which is positive 12 centimeters. When the object is placed 36 centimeters from the mirror, so here object distance, object is always on the left side, which is negative, so minus 36 centimeters, and you are asked to calculate the focal length. So focal length is what we require. So this is a direct application of the mirror formula. 1 by f is equal to 1 by v plus 1 by u, which is 1 by 12 plus 1 by minus 36. We can write it as 1 by 12 minus 1 by 36. The LCM is 36, right? So here it is 3 minus, here it is 1, which is equal to 2 by 36, which is 1 by f. Therefore, f is equal to 36 by 2, which is equal to plus 18 centimeters. And our answer is correct because focal length is always positive in case of convex mirrors.